Okay, for introduction, matrices are essential mathematical structure that consist of rectangular arrays of number, symbol or expression arranged in rows and columns. They are widely used across various disciplines including physics, computer science, engineering and economics due to their versatility in representing and solving complex problems. Matrices come in different types such as square matrix, diagonal matrix and identity matrix, each serving specific purpose. Fundamental operation with matrices include addition, scalar multiplication, matrix multiplication, transposition, finding determinants and inverses. This operation enable the manipulation and analysis of data in numerous applications, from solving system of linear equation and transforming graphical image to encryption in cryptography and modeling economic system.
In 1848 England, the Steve first introduced the term metric, which is the Latin word from "verbum" as a name for an array of numbers. Metric algebra was nurtured by Word for Arthur Clay in 1855. Clay studied computation of linear transformation and was led to define metric multiplication so that the metric was coefficient for the composite temperature. St is the product of the metric for S times the metric of T. Next, the Chinese studio metric, especially the Babylonians, also studied them. Confucianism was a mathematics was carried to theory of metric. Internally, he extracted coefficients from linear equations and organized them into a metric.
For the next one is application. The application we use is image processing. We have 3 points. The first point is image representation. Image as a metric, each element is pixel, intensity or color. The second one is image filtering. Filter modify image through metric multiplication, and filters can have positive or negative value and variance size. And the last one, convolution operation. Combine array to enhance and filter image. Kernel slide over the image to extract a feature. The next slide is a picture about image processing.
Example of image processing is kernel. Techniques such as blurring, detection, and sharpening. Simplify a two-dimensional metric of number. Operating on this pixel value using straightforward mathematics to construct a new image. Kernel has specific properties depending upon its value. The position of the kernel, which is above the current output pixel. This could be outside of the actual kernel. Tools usually corresponds to one of the kernel's elements. For a symmetric kernel, the origin is usually the central element. This is example of different picture before and after use the kernel application. Gaussian blur. This kernel is similar to the blur kernel presented above, but it's different in that it is dependent upon the Gaussian function, a function which creates a distribution of value around the center point. This result is a kernel in which pixels near the center contribute more toward the new pixel value than those further away. Next, sharpening. This kernel sharpens an image, accentuating the edges of the image. Sharpening an image adds contrast to edges, and a 3x3 version of this mask is similar to the edge detection kernel with a center value of 5. This adds contrast around an edge by accentuating bright and dark areas. And lastly, unsharp masks. Used to sharpen an image This technique is based upon first creating a Gaussian blurred copy of the image. This blurred copy is then subtracted from the original pixel above a given threshold are sharpened by unhatching light and dark pixel.